Okay, so today I'm going to cover 4.6 and 4.7 probably. Okay, so and then the uh, in particular this course, I mean statistic for science engineering, the textbook is really good. So I strongly suggest you to read the textbook. So because I told you several times in class, the all examples. I'm gonna go over all the examples. Um, in the textbook. So um, please read the text, the examples, um, and list before listening to my this video lecture. Okay, and then the from the 4.6. I mean, from the 4.7, we're gonna study some specific popular continuous the distribution. So then I'm gonna cover 4.6 quickly, and then we see I'm gonna focus on those particular but popular continuous distribution. Now the 4.6. Okay, so 4.6. The To understand the 4.6, we need to you need to know the normal the probability distribution and standard normal probability distribution, what we learned in 4.5. Okay, so before going over before the watching this video, please review 4.5 first. Okay, now then 4.6, what we're gonna do, we're gonna approximate um, the binomial probability distribution. That's the one of the popular of the discrete distribution, discrete random variable, right? So we're gonna approximate the binomial probability distribution using normal distribution. Okay, so the normal 0.6, and then approximation to the binomial and Poisson. Oh, distribution. Okay, so idea is this: the normal distribution can be used to approximate binomial probability for cases in which n is large. Okay, n is not just 100, maybe more than 10,000. Okay, so while we are able to use normal distribution uh, to approximate binomial probability because see example 4.13. Let me try to share the textbook. Okay, so let's see. Uh, Give me a second. Okay. So now, see in the example 4.13, see, assume that in a digital communication channel, the number of bits received in an error can be modeled by a binomial random variable. Okay, so that we have, what's a trier? The what we check the whether or not the communication channel receive error or not. So that we have only two outcomes. We get the the bit receives error or not, right? So they assume that the probability that a bit is received in error is 1 times 10 to negative 5. If it's 16 million bits are transmitted, it's really huge, right? What is the probability that 150 or fewer error occurs? So let the random variable x denote the number of errors. Yeah, number of error right there. Yeah, I know it sounds weird, but let's say number of success in this problem means number of errors. Okay, then X is binary random variable, right? So then the here total number of try are going to be 16 million, right? The total number of the bits received error is X, right? And then probability of success is going to be 10 to negative 5 because the bit is received in error is what? 1 times 10 to negative 5. Okay. Then Q, which is the probability of failure, going to be 1 minus the probability of success. Right. So see this one? Okay. Right there. So now then what? Yeah, so we got the kind of formula, but in in practice, it's really difficult to compute. You see, 16. Even the computation of this combination is really tedious. So that's why we're gonna use normal approximation as to approximate binomial distribution. Okay. So now then, what are you gonna do? So the normal approximation. I mean, if yeah, so if x is a binomial and the random variable, right, with parameters n and p, then z is equal to, you see the z score, right? Okay, z is equal to x minus n times p. Or is it n times p? N times p gonna be what? The mean of the binomial distribution, right? Over the square root n p q. Okay, so then that is approximately the standard normal random variable. That is, oops, let me write in here, is approximately standard normal random variable. Okay, so then to you see the approximate, right? Okay. Um, now then to approximate to approximate the binomial probability with a normal distribution. Give me a second. We have to apply the continuity correction. Okay, so because what, since this x is the discrete random variable, right? And then but now this one z score, this is the continuous random variable. So there is a gap between discrete random variable and continuous random variable, definitely, right? Because the discrete random variable is just in the binomial distribution, the x must be 0, 1, 2, 3, 4, 5. This should be the non-negative integer, right? So what about z? Z is a continuous random variable. So there is a gap between two random variables. So we have to apply, we have to reduce a gap. Okay, so that's the continuity correction. Okay, so what that means, the the x is less than or equals x. Okay, so what keep in mind this is what? Binomial random variable. All right, this is equal to probability that x is less than or equals x plus we put 1.5. Okay, all right, so that 0.5, that is called continuity correction. Okay, so now then let's see, this is equal to, okay, the probability that z, I mean, so this is a binomial, random variable, okay? Then that z, this is z-score, I mean continuous random variable in a standard normal distribution. This is less than or equals, and then x plus 0.5 minus np over, and then the square root npq, okay? Oh, sorry, right here, okay? So now then, what if we want to find the probability x is greater than or equals x? Okay. So then sorry. So probability x is greater than or equals x. This is equal to probability that x is greater than or equals x minus 0.5. Okay. I mean this is one, and this is second case. Then oh, this is not equals approximately. Okay, approximately. Okay. Then probability that z is greater than or equals, right? Greater than or equals x minus 0.5 and then minus np over square root npq. Okay. So why we have to add a 0.5 and why we have to subtract 0.5 in second case? Because look at this. Let's say here for example, let's say this is the specific value of random variable, okay, x. Let's say, for example, just 5, okay? All right, and there is then 4. This is a 6 right here, okay? And then the probability that x is less than or equals x, 5, is this, right? Actually, not that one. Actually, what? Here's a 0, 1, and 2, and 3, and 4. Just 1, 0, 1, 2, 3, 4, and 5, right? Okay. But the what? The when we transform the discrete random variable to the continuous random variable, then 5 through 6, all the random variable 5 through 6, we may lose the probability that x is between 5 and 6. Because since the x is a random discrete random variable, we don't get the probability that x is x is the number between 5 and 6, right? So we add 0.5 up to here. Okay. All right. So now, anyway, so now then let me see. So this approximation is good for n times p is greater than 5, and the n times q is greater than 5. Okay. So the approximation is good for n times p is greater than 5, and n times q is also greater than 5. Okay. Then let's see example, the textbook. Okay. Oops. Yep. All right. So 4.15 and 4.15, yes. So again, consider the transmission of bit in example 4.14 to judge how well the normal approximation works, and assume that only n equals 50 bits are to be transmitted, and that the probability of an error is p is 0.1. So the exact probability that 2 or fewer error occur is, yeah. So here we want to compare the probability, exact probability of the binomial distribution and then approximation using normal distribution. Okay. So probability x is less than or equals 2 gonna be this, right? Because what? Probability x is less than or equals 2 means the probability x equals 0 and then x equals 1. So combination 50, 0, and the 0.9, the fifth power, that's the probability x equals 0. The combination 51 and 0.1 times 0.9 to the 49th power, that's probability x equals 1 in the binomial distribution. Okay, and then now, so we got 0.112, by the way. And then wanna use the normal distribution to approximate that binomial probability. Then probability x is less than or equals 2 means that what? G-score, this is the G-score, right? This is G-score corresponding to the random binomial random variable x. And less than or equals 2.5 minus 5. You see that? 2.5, where that comes from? We add 5 into 2 right here. Okay. So then divide by square root and n times p times q. All right. And then I told you, so we can find out the that probability using calculator TI-84, right? Okay. So I'll show you how can you find out this. Some of you may forget it, right? So here, you can use table, but can you see that? Oh, okay. Can you? Yeah. Yeah. This is. I think this is better. All right. So we go to the distribution. Okay. Press second, and then VARS. Then you see the normal PDF or CTF. We use normal CTF. Okay. Because we want to find out what probability that x is less than or equals to. Okay, is equal to probability that z-score is less than or equals 2.5 minus 5 over square root 50 times 0.1 times 0.9, right? Okay, so then is approximately what? Probability that z-score is less than negative 1.18. Okay, so we use the normal CTF. The lower gonna be negative 999, right? So negative 99999. Okay. So then upper gonna be negative 1.18, right? Negative 1.18. And then U gonna be, because this is a standard normal distribution, so U must be 0, right? And then sigma standard deviation gonna be should be 1. And then paste it. Oh, clear. Okay, negative 9. Yep. So I got 0.11900, so approximately 0.119. Okay. So now share screen. All right, so we got the 0.119 right here. Okay. So let's see. Similarly, you see that we can also approximate probability x equals 5 as like this. Probability x is between 5 and 5. Okay, so then we add 5 into the 5 in the right hand side, and then we subtract 5 into 5, which is in the left hand side. So probability x is between 4.5 and 5.5. And then convert this onto z-score. Okay, and then using the calculator, we can find out the probability. Okay, so now next one is which one? Yes, the let me skip the example 4.16. I'm sure that you can also figure out. I'm sure you can figure out this problem, which is similar to 4.515. Okay, so next one. Let's see. Oh yeah, so Next one is normal approximate to the Poisson distribution. Okay, so in chapter 3, we learned the Poisson distribution, right? So we can approximate Poisson distribution using normal standard normal distribution. So next one is normal approximation. Poisson distribution. Okay, so if x is a Poisson random variable with expected value is a lambda and variance is the lambda, then the z-score going to be x minus lambda over square root of lambda. Okay, that is approximately a standard normal random variable. A standard normal random variable. Okay. So it's the same continuity correction used for the binomial distribution can also be applied. So the approximation is good for lambda is greater than 5. Okay. So now 1, 7. Let me see. Oh, yeah. Let's see example. Okay. So share screen. All right. So yeah. So let's see example 4.16. Okay, normal approximation to Poisson. So assume that the the number of asbestos particles in a squared meter of dust on a surface follows a Poisson distribution with a mean of 1,000. So if a squared meter of dust is analyzed, what is the probability that 950 or fewer particles are found? So then the what? So in this problem, lambda must be a 1,000, right? Okay. So and then let me see, and then the the length in this case, the area is right. The area is just 1. So the as you can see, the probability that x is less than or equals to 950 going to be sigma times e to the negative lambda t times lambda t to the x power. So here t must be 1, right? Because here no, t means a length, but in this problem t must be um, the area, which is just a square meter, right? Is 1. So we, the so we got this one, and then we gonna find out, we're gonna approximate this one using the standard normal distribution. So we're gonna find the z-score. Okay, I mean transform the random variable to x to the z-score z. Then we add 0.5 into 950. Okay, this approximately is equal to probability that z is less than or equals 950.5 minus 1,000 over square root 1,000. Okay. Yeah, no, no, it's not a big deal to figure out decimal expression of this fraction, right? Which is negative 1.57. Okay, and then using the calculator TI-84, okay, go to distribution, and then using normal CDF, okay, and then you can figure out. Keep in mind, this is standard normal distribution. It means that the mean mu must be 0, and then the sigma, which is standard deviation, must be 1. Okay, so then using calculator, you can get this one. Okay, so let me stop here. Then I'm gonna the next video I'm gonna cover the section 4.7. Okay, All right.